Hello. In this video, we'll talk about Wilson's theorem. Yeah. So Wilson's theorem says that for a prime P, um, P minus 1 factorial is congruent to -1 mod P. So let's just see, is this true for some small values, right? Um, well, 1 factorial is congruent to -1 mod 2. 2 factorial is congruent to -1 mod 3. 4 factorial is 24, is congruent to -1 mod 5. And 6 factorial is 720, which is congruent to -1 mod 7. So yeah, looks good. So let's see if we can prove this. So let's just take 7 as an example. So 1 times 2 times 3 times 4 times 5, 6. So we want to see why is this -1, right? Well, it turns out that every number mod, every non-zero element in prime modulus has a unique inverse. And in fact, its inverse is different than itself, unless it's plus or minus 1. Why is that? Well, like if x squared is congruent to 1 mod p, then x minus 1, x plus 1 is congruent to 0. But the only way two factors multiply to 0 in a prime modulus is if one of the factors is 0. So x has to equal 1 or -1. So the only square roots of 1 are 1 and -1. Everything else has an inverse, but it's different than itself. So for instance, 2 is the inverse of 4, and 4 is the inverse of 2, mod 7, because 2 times 8 is 2 times 4 is 8, and 8 is 1 mod 7. Similarly, 3 times 5 is 15. 15 is 1 mod 7, so 3 and 5 are inverses. So when we multiply everything together, everything will be paired with an inverse except 1 and -1. So we have a product of a bunch of 1s and -1. So the product has to be -1 mod 7. And this would generalize to other primes as well. So yeah, proof by example. But it generalizes perfectly. Okay, so one application of this is like it's well known that if P is 1 mod 3, 1 mod 4, then -1 is a quadratic residue, meaning it's a perfect square. So there is some solution to like x squared. So exists solution to x squared congruent to 1 mod p. But what is that solution? Well, Wilson's theorem lets us find an actual solution in addition to this fact. So if we take 13, for example, like Wilson's theorem says 1 times 2 times 3 times. So 12 factorial is congruent to -1. So uh, We can rewrite this as so 6 factorial times 6 factorial times -1 to the 6. If we factor out, a -1 from each of these, is congruent to -1. But hey, that means that 6 factorial squared is -1. So 6 factorial is a solution to x squared congruent to 1 mod 13. How did we get 6? Well, 6 is, this is like half of 12, and 12 is 1 less than 13. So it's the prime modulo minus 1 over 2. So in general, p minus 1 factorial, p minus 1 over 2 factorial is congruent. So this squared is a square root of -1. This number is a square root of -1. So it's, yeah. So that's kind of, yeah. So I think this is a really like cute or beautiful fact, or like, like it's a really not only like, so this proves that -1 is always a quadratic residue mod p when p is 1 mod 4. Why do we need the condition 1 mod 4? Well, if p was 3 mod 4, then let's say we have 7, right? So 7 is 3 mod 4. Then what goes on wrong in our proof? Well, this would be 1 times 3 times 3 times 4 times 5 times 6. So this is 4, 5, and 6. If we try the same thing, this time we have an odd number of -1s. So 3 factorial times 3 factorial times, if we factor out a -1 from each factor, it's -1 cubed. So this is equal to -1 by Wilson's theorem. Well, yeah, so now this just says 3 factorial is a square root of +1. So, I guess we can write this as an intermediate fact. So p congruent to 3 mod 4 implies p minus 1 over 2 factorial is like solution to x squared congruent to 1 mod p. So so at the very least, p minus 1 over 2 factorial is a square root of -1, which we saw that it means it's plus or minus 1. And maybe we can say more. Yeah, so Wilson's theorem is useful in a lot of other contexts, and like it's used in many proofs in number theory. And yeah, there are other proofs of it as well.